right, good afternoon. You guys seem a little sedate. There's no recent exams to talk about, or was 3 this week? Okay, so just kind of dead, huh? Yikes. Okay, so I was way off. All right, so I posted the Excel homework assignment. You probably saw that. I'll talk more about that in the next lecture because we're going to go through some Excel and kind of build a similar, very similar document for a very similar problem, and then let you kind of use that as a launching point to do your own spreadsheet for that assignment. Yeah.
Should we start the homework before that lecture?
I think it's a good idea. Yeah. Like I do with a lot of these example problems, I think you benefit best by giving it a shot yourself and seeing where you get lost and like trying to piece it together. But, you know, for the sake of this Excel assignment, if it's not clicking, don't spend 10 hours trying to make it click before we talk about it. That's kind of thing, right? If you can struggle through it for half an hour, an hour, and then you solve it and you're like, great, now I'm just going to show up to class and do my other homework and kind of watch, make sure I got everything right. Maybe that's perfect, right? But if you give it a little time and you can't figure it out, then you come to class and you know, oh, I didn't figure it out, so that's why. Okay, got it. So that's my opinion. So I'd suggest that, but we'll talk more about that next time. I think it should be pretty related to what we were doing right after the first exam. Some of that solver stuff and okay, find a pH given an electroneutrality balance, and then you add in the mass balance and stuff to put an equation together to solve for zero. It's going to be that type of a problem, and using Excel to do that. So we're kind of going back to that. Bit more complicated than what we've already done in class, but you'll see that. Relates a bit to this, and maybe we could even use this type of math that we covered last time to tackle it as well. But as I said, we'll kind of stick with that assignment. Okay, so we left off here last time, and what we're really working towards is understanding on a graph how we can extract information about a system that we want to solve for pH or something. And we're moving towards, okay, well, how do we know how much acid or base would we need to add to move a system from point A to B? And what can we learn from the system about that? So there's a few things that, you know, before I even dive into this example, there are a few things we might be very interested in getting a handle on in terms of the information within a system, given that we can do what's called titration. One would be the total amount of some acid or base in solution, that AT. A lot of times we're given that value, but if we can solve everything else about the problem, maybe we can discover that, right? Maybe we can solve for AT given an experiment. That's in fact, if you've taken probably general chemistry or like the Gen Chem lab, you've probably done some sort of titration. And technically, this is what you were doing. You were solving for something that changes when you hit a certain pH, and you were quantifying how much acid or base did you need to add before you hit that point. So we're going to connect those today. So the A total would be one of them. And then we could look at, of course, the pH itself. Maybe we could solve for something like a Ka value. There are a few pieces here where we can move around and figure out. Okay. And hello online. All right. So this example, last time we covered a separate example, kind of looking at a pretty simple system. Here we have, we want to know the pH of an equimolar solution of ammonium chloride, NH4Cl, and sodium acetate, NaAC. Both of them are 2 times 10 to the minus 2 moles per liter in water. Okay, so we have the same amount of NH4Cl, so we can say the concentration of Cl minus is going to be equal to the Na plus, right? just because we know we've added some amount of NH4Cl and the same amount of NaAC. Now the ammonia, NH4, is going to be in some equilibrium, and the acetate is going to be in some equilibrium. We've looked at both of these before, and we recognize the ammonia can act as a base. It's kind of a weird one, right? It's going to be NH4 plus. It can give away a proton, so it becomes NH3 uncharged, and then the acetate, acetic acid, that's vinegar, we've also talked about a little bit to say that that can look like this. A pretty good example of a generic HA acid, right? So both of them can act that way, and we've got both of them in the solution. So can we find the pH given those parameters? That's kind of the question. Okay, so I've got the solution up here that we can talk through. So because Na and Cl constitute a neutral salt, sodium chloride we could have added in that form, they're essentially not doing anything. They're both going to be spectators, right? The Na and Cl. So in a way, it's as if we added some hypothetical NH4AC, right? And so for every molecule of NH4, we added a molecule of the acetic acid, or AC, acetate, I guess. So ammonium acetate is kind of the equivalent thing that we've added. So to solve for the pH here, we have to draw both of those curves on here, the ammonia curve and the acetate curve. So you see here we've got the ammonia drawn here. That's ammonia and ammonium ion here, like that. And then in addition, we've got the acetate drawn here, and of course its corresponding acetic acid here. So we've got both of those drawn, and then we are given the N total, or A total, like we could say. So N total for the nitrogen, for the ammonia, equals the AC total, which is 2 times 10 to the minus 2. So that's giving us a total here. Now, one thing I'll notice here is each one of them has a total there at 2 times 10 to the minus 2. So this would be, like this line right here would be 1 times 10 to the minus 2. So we're just a little bit above that, right? So just putting a little reference on the graph there for us. Okay, so we're just a little bit above it, and the max that either get to is at that threshold. Okay, so then we can write up a proton balance to say, okay, if we look at an equivalence point somewhere, and we're kind of looking for that type of a thing in the system, what is the proton balance? So we have the sum of the OH minus generating species on the left and the H plus generating species on the right. So we could say to get H plus, we have to release an OH minus, so we have H plus on the left, and to get an HAC, we had to also kind of release an OH minus from water to grab that proton. So those two are on the left. Likewise, the NH3 and the OH minus are on the right. What we'll notice is neither the NH4 plus or the AC minus show up in our proton balance, right? Because we added the stuff in those forms. So they can't be in the proton balance because it didn't require any change in order to have them in solution. These guys had to have some sort of change to have them in solution, right? A change of proton one way or the other. So on the left, it's kind of like we grabbed a proton from solution. On the right, it's kind of like we added a proton to the solution. All right, so in the proton balance, that's the way it shows up. And then we could take a look at different areas of the diagram and make some kind of shortcuts for this proton balance. Okay, so for most of the diagram, we'll recognize, let's just take a look at the left side of the proton balance for a moment. we'll recognize that the HAC should be a lot larger than the H plus. And we can simply look at it in terms of we have the H plus line drawn here. And then we also already drew up the HAC line. And we can see for almost all of it, up until we get around this region, we are at least an order of magnitude or two larger, right? The HAC is larger. So the HAC then is dominating the left side of this equation for almost all of it, okay? We can kind of do the same thing on the right side to look at the comparison of OH minus and NH3. Here's our NH3 and here's our OH minus. And what we'll see is the same exact thing up until we get to somewhere around here. The NH3 is the dominant one of the right side of our proton balance. So it's kind of like for a lot of this, these two drop out unless we're on the extremes. So with all of that, if we're anywhere near neutral, the balance becomes the acetate is equal to the ammonia. And that means where those two cross is the pH that we're going to land. So if we just added these two to solution and they are drawn up accordingly to this graph, you know, we had to put the pKa's where they're supposed to be, and I'm just assuming that they plotted that appropriately. Then we look at where these two cross, the NH3 and the HAC. Turns out that's right at pH 7. Okay, so graphically speaking, this one is a kind of an interesting one to look at, where everything lines up. If, you know, because these are the only things in solution, we've not extremely changed the pH one way or the other. These assumptions hold valid, and then these two are going to be equal, and when we find that equal point, it's at pH 7. Okay, that could change, I think, if we had something that had a bit of a different pKa. So it might not be pH 7, even though that feels like it should be. I think this is a special thing between ammonium and acetate. The pKa's, I think, are the same distance or approximately the same distance from 7, from pH 7. Okay, does that make some sense?
So this, like that, like full intersection point at pH 7, that's not where both of those pKa's are equal to pH, like simultaneously?
Well, let's look at one pKa or the other, right? So one pKa shows up right here. This one's for the acetic acid. The other pKa is happening right here. And if we look, pH 7 is kind of right in between those two. So if we shifted both of them to the left, we'd probably end up with a different pH as the point where they intersect. Does that make sense?
Okay, yeah.
Even if we shift one of them one way, that would probably shift the midpoint where they cross.
Right, so that's like essentially the equivalence point.
We have to be careful with that term. Equivalence point is specifically referring to when we're taking one acid at a time, how much acid did it take to get us to the point where that particular one crossed. The HA equivalence point is where it crosses the H plus line, which in fact that would be this one, or and this one. We're going to talk a little more about equivalence points, so we'll come back to that. Okay, good. All right. So I mentioned last time, and I talked about it, but I didn't quite get to this slide. When we did that little titration in my home lab, we saw the color changing because we're moving the pH and something in the water is responding. Now, if I did this over and over again, I would dilute the thing and maybe the color wouldn't change so strong, but still adding the acid or the base would still have that. We would still see that, and eventually I'd have to pour it out and start over. But we can add a small amount of acid or a small amount of base, especially if it's concentrated, to make that shift, and it's not really changing too much that solution. So we're going to talk about that process, how we quantify it, how we look at it on a graph, and so that hopefully we can put that to use and at least better understand what was going on when we did some Gen Chem labs. Okay. Okay. So one little note here from one of the textbooks I'm drawing from. If we started with a solution of acetic acid, HA, where the concentration was 10 to the minus 3, we could ask ourselves how much sodium hydroxide, NaOH, needs to be added to move from some different point to some different pH. And what is the new speciation at that spot? So to solve how much of our acetic acid is in acetate versus acetic acid, right? We could look at all those pieces. So coming back to where I started from the begin with, the total amount of acidity, the pH, the Ka, maybe we can say the alpha fractions. All of those are things that we may be interested to describe to understand what all's in the system. Okay, so equivalence point. We just mentioned this a moment ago, and we talked a little bit about it last time. This is a very specific definition. It sounds like it should be that point where they cross, but the spots where we cross things on the graphs are usually more like an equilibrium or a, where those two came across. Not every time we have something cross, we call it an equivalence point. I guess generically we could call it that, but we reserve this terminology in the chemistry for specifically the HA or the NaA equivalence points. And it's kind of like the end point of titration towards the acidity or the end point of titration towards the basic. Okay, that's one way to think about it. We can go beyond that end point. That is certainly possible, but by getting to that end point, we've characterized our system, as we'll see in some of the graphs today. It's where the interesting stuff stops happening. Okay, so we define it as the HA equivalence point is if we started by adding NaA. So we start with A minus. We've added NaA, some generic acid, to water, and that's going to be releasing Na plus. So I'm going to say it this way. That's just going to be releasing Na plus and A minus. Then we're going to have HA in equilibrium with H plus and A minus. Now what you'll notice is if we add it in the form of NaA, we're not really adding much H plus. And because we are forming some HA to some extent, we are actually taking H plus out of the water if we add it in the form of NaA. And you'll see this if you ever look at a chemical bottle that says something like sodium phosphate monobasic. That monobasic is referring to exactly this. Some of it's adding as a sodium, and so it's at least a little bit basic. You could have dibasic sodium phosphate. That means there's two sodiums. It's kind of a double basic, because that sodium is kind of giving it a basic characteristic, because it's going to snatch some protons. Whenever you form the phosphoric acid version of it, you're snatching some protons away. Do you have a question?
Yeah. So you're saying that, like, generally with the equilibrium of HA, H plus plus A minus, that whenever you add NaA, that you're like essentially like overloading the vessel with the conjugate base, which would like form the acid.
Yeah.
Is that what you're saying?
Yeah. So whenever you add an acid, an acidic species, one way or the other, even if it's in the conjugate base form, it's going to find equilibrium. Now, if it's in a very strong acid, you're probably not, right? So if you add, so a good example is sodium chloride, right? If you add hydrochloric acid, HCl, you're certainly adding protons. If you add the conjugate base only, NaCl, you're not really doing anything to the protons balance, because the Cl minus is not going to form HCl at any pH within the 0 to 14 range. Because the pKa is so low, you're not going to get any meaningful amount of HCl in that solution. So in that case, the conjugate base doesn't matter. It's such a weak base, you're not going to have any of it. It's not going to take any action. But for a weak acid or an acid that has a pKa within the 0 to 14 range, then that's going to happen. I hope I didn't just confuse that further for you. We're going to talk a little bit about the spectator ions in a couple minutes. Okay, so the HA equivalence point is as if we started with just NaA, so we're kind of in a basic situation, and then we add enough strong acid, something like HCl, to get us to the HA equivalence point. And what I'll flip back to this for a second. So it's as if we started by adding just NaA, which would, in the case of our acetate, would start here, and we want to go to the left until we reach the point where we cross right here. So the change from this point to this point is the amount of acid we have to add. That's kind of the definition of our equivalence point situation. I think I've got more graphs that'll be a little cleaner to write this on in a minute. So that's the definition. So as an example, both of the following solutions are at the HA equivalence point for an acetic acid system. Let's say we have 10 to the minus third formula weight, that's just moles per liter, of acetic acid in 1 liter. So that's system number 1. We just added 10 to the minus 3 moles per liter of HA with acetic acid, so I'm going to say HAC. And then the other one was 10 to the minus 3 moles per liter of NaA, well, NaAC in this case, of sodium acetate, which that's that conjugate base amount, plus we have to add 10 to the minus 3 moles per liter of HCl. So the 10 to the minus third HCl is going to give us the same amount of acid, the protons, that we're missing from the NaA addition, right? In both cases, we have 10 to the minus third moles per liter of acetic acid, total, AC, AT for the AC molecule, and 10 to the minus third H plus. Okay, so both of these systems have, both have 10 to the minus third AC total and 10 to the minus third H plus.
And that's because, like, whenever you're adding strong acid, it fully ionizes and it doesn't ever go back to HCl.
Exactly.
So then, okay, yeah. So that's why you would need to add acid, like using
A strong, yeah, very strong acid. Okay. Does that make sense? So again, we're just defining how much acid it's going to take to go between these 2 points. Now, from the proton balance, we could say H plus is equal to OH minus plus A minus. And if we have this acidic solution approximation over in that acidic condition, we can neglect that OH minus. And so that's where we get this relationship between H plus and A minus. Going back to the graph, we looked at where H plus and A minus crossed, and we called that the equivalence point. So that's mathematically where that comes from. Okay. So here are some graphs to show that a little more clearly, and also give a few examples of when it works well and when maybe that approximation doesn't work so well. So for a moment, let's take a look and look at each spot where these cross. Okay, so we have, and I think I noted the wrong spot earlier. So we have A minus is equal to H plus. I drew that wrong earlier, but just rely on this graph. So it's A minus, this guy crossing H plus. It's happening right here. We can do that on each of these graphs. And these graphs are showing different starting concentrations and different pKa's. So A and B have the same pKa, but different starting concentrations, 10 to the minus third or 10 to the minus fourth. And this guy has a pKa that's shifted a bit. So what we can notice is these factors will move the equivalence point a bit, and in some cases might call into question whether or not we can make this simplification. So in general, I'm not planning for us to think too hard about that, but I'll just read this real quick. For example, the HA equivalence point, we can see that the weak acid approximation is reasonable for cases A and C, but not so good in this B case where the equivalence point happens pretty close to that pKa. So maybe we have to do a tiny bit more math in that case, but okay. But don't worry too much about that. We're not going to mess with that too much. Okay, so basically already said just about all of this, but I'm going to elaborate a little bit. Here's the electron neutrality, mass balance, and proton balances for, so we did the HA equivalence point. Here's the NAA equivalence point. So we have solution of NAA at its equivalence point, and we get there by starting at the HA equivalence point and adding enough enough base to get us to the kind of the inverse spot. So we're going to add something like NaOH, sodium hydroxide. That's going to be a very strong base so that NaOH will completely dissociate into Na plus and OH minus. Okay? Just like our HCl is completely dissociating. So our electron neutrality balance for this scenario is going to be the cations on the left, H plus and Na plus, and the anions on the right, OH minus and A minus. We can do some mass balance equations as well, and we could get excuse me, the sodium equal to the A total. In this case, if we added it as NaA, or excuse me, if we have, even if we start with HA and we added enough NaOH to get to this NaA equivalence point, then we actually know that there's the same amount of sodium as the total acid, because we literally had to equal that out on the electroneutrality side of things. We can see that coming through because every time we add an Na plus, that is accounting for an A minus here. So the two mass balances we can simplify like this, and then we say H plus plus HA is going to also be equal to OH minus. All right, the proton balance. With the basic solution approximation, we will find that HA is approximately OH minus, and that's why we would draw the NaA equivalence point where those two meet. Okay, where the HA is typically drawn like that, and we know the OH is drawn that way, so we find where those two intersect, and that's our NaA equivalence point. So we'll back up to this graph and say the HA and the OH minus, this line, those meet here, here, and here. Okay, so we can always kind of double check to see, does that basic solution approximation look good? In these cases, it seems to look pretty good. This middle one, yeah, it's probably okay. Okay, let me go back. All right, so one thing that I kind of hinted at a moment ago, but I want to expand on, is the fact that that sodium that we're adding can be a very nice tracer for us. It doesn't even have to be sodium. It could be calcium. It could be potassium. You know, we have potassium hydroxide. It's really a spectator ion can act as a tracer for us if we know how much is there or if we know how much we added. And this relates very much to the concept of what we say alkalinity. So we'll come back to that a little bit, even though we're not going to dive into the carbonate system today, and that is also relevant. We're going to kind of lay some of the groundwork for all of that. So sodium as a tracer for the strong base. Now the obvious thing here is we often use sodium as like sodium hydroxide, right? Then of course every time we're adding some hydroxide, we're adding some sodium. So in that sense it's kind of obvious. But with a bigger picture, anytime we want to change pH without changing the amount of some acid that we're dealing with, let's say acetate, if we want to change the pH without changing the amount of acetate, well, we have to add some other strong acid or base, right? And so when we do that other strong acid or base, whether it's HCl or NaOH, our electroneutrality is going to look something like this. H plus Na plus is equal to A minus plus OH minus plus Cl minus. So let's say we add a little bit of HCl and a lot of NaOH, right? Then we're going to have all these species here. So we've been adjusting the pH back and forth or something with HCl and NaOH. These are the things we have in solution. So in this scenario, the Na plus concentration is going to trace exactly the amount of strong base that we have added, whether that's in the form of NaA or in the form of NaOH. So every time we've added some sodium, it's essentially tracking how much strong base we've added. Now, conversely, the Cl minus is going to trace how much of the strong acid we've added. So they can counterbalance one another, but you'll see they do just that if we have some of both, right? They're both there. That's because we have no other sources of the two aside from, in this system, aside from if we added this stuff as NaA, or if we added NaOH or HCl. Okay, with that, we can write an interesting equation here. We can say that the H plus some strong base, and right now we're just substituting the Na plus, is equal to the A minus, that's the alpha 1 times A total, plus OH minus, plus the strong acid that we've added, Cl minus. If we write it this way, we can then kind of isolate the two things, these two tracers, so to speak, that are just spectators. We've added them, they dissolved, and then they're just sitting there not doing anything. Okay? All of these H plus related stuff, the H plus, the OH minus, the A minus, any other acids or bases that are doing stuff, all of those are actively changing. But the Na plus and the Cl minus, they're just sitting there until we add a little more, right? So they just sit there spectating, and if we collect those on their own, it's actually really convenient because that gives us a lot of information about what's on the other side of the equation. So if we just simply say, well, what if we do Cb minus Ca and set that equal to this alpha 1 At plus OH minus H plus, what we suddenly find is the right side of this equation is kind of looking like how much base do we have in there, and the left side of this equation technically is saying the amount of base minus the amount of acid we have in there, right? So by looking at the spectators, we can know what's going on with the action side. And so it becomes a very convenient way to look at chemical systems to understand the kind of the total cations, or the net charge, of the spectators is going to be equal to the total amount of base. So we could have a negative number, so on the right side of this, if there's a whole lot of H+, if it's very acid, then the amount of base minus the amount of acid should be a negative number. It's a lot of acid. And on the right side, we see, oh yeah, H+ is dominating. That's a negative number. And so it can make sense. This is what we're going to call, and I guess I've just given myself some more space to elaborate, net strong base. So Cb minus Ca would be the net strong base. And this number can be negative if a negative net strong base means we have a net strong acid. Okay, and so we could define all of this as a net strong acid, and then the inverse would be a base. You get the picture, right? But the point is, what is the left side of this thing tell us about everything else? And so if we identify the spectators on the left and the, I don't know, I'll say dynamic species on the right. If we separate them that way, that's where we get Na plus minus Cl minus equals this A minus plus OH minus minus H plus. Now the interesting thing is we could add other stuff. So an example of making it more complicated would be to add in the carbonate system. So let's say we have Na2CO3. Okay? We've got this sodium carbonate, bisodium carbonate, whatever its formal name. What we're going to end up with, we're going to say that's in water. Okay? What we will end up with is Na plus on the left. There's no Cl minus in this particular solution. And on the right, we get, well, what is A minus? Technically, we're going to have HCO3 minus. We will also have, and I think since we're doing this from a charge balance perspective, we need 2 times the CO3 2 minus. Of course, we're going to have OH minus. And we will have the H plus. So that would become our equation for alkalinity.
And this is the electroneutrality equation?
This is coming from an electroneutrality equation, right? So the electroneutrality equation, we could write that up too. So for this system, the electroneutrality would start at H plus Na plus, right? We have some concentration of it, equals HCO3 minus plus 2 CO3 2 minus plus OH minus, right? Let's pretend I didn't squish that in there so bad. So from the electroneutrality equation, we could just rearrange and isolate the net strong base, right? So if we added other stuff into this equation, if we added some acid, we could certainly subtract the Cl or some other species here. We could add sulfuric acid and then we'd have a sulfate on the left. You can see how we can arrive at this equation that describes all that active stuff on the right and all the inactive stuff on the left. And that's going to tell us something as a function of pH, which can be very convenient, as you already know. And this is really how we describe alkalinity. Now, a lot of times in a natural water, we're going to have calcium and magnesium and things like that. And so we can set up an equation where we can know how much acid buffering stuff is going to happen given how much of these ions we have, these cations. So I'm going a little bit ahead of myself here in terms of kind of explaining why and when this is relevant. But my point is these species on the right are all in equilibrium with some other H plus species, right? So all, I'm just going to call it H plus active on the right side of it. Everything on the left side is just spectating and just hanging out, right? Not interacting with H plus at all in terms of any meaningful equilibrium. So another way to write that down here, in other words, the sum of the conservative cations minus the conservative anions on the left side, and on the right side, the sum of the bases that are titratable with a strong acid. So if you look on the right side, if we add a strong acid, each one of these could be titrated, meaning we could get rid of it. So a negative acidity here we could get rid of by adding acidity. So we can account for that negative by adding acid. For each of these other ones, you'll notice if we added more protons, we could get it to a point where there's no more charge. Okay, so we could change HCO3 minus to a neutral by adding enough acid. It's going to change it all to H2CO3. That's the titration that I'm talking about. We could add acid to OH minus to form water. That would be the titration of the OH minus. We can titrate the CO3 2 minus by adding enough acid to push it all the way to H2CO3. So that's when I say everything on the right of this is titratable, it's going to interact with a strong acid and drop out of this equation from the charge perspective. Okay, and if we look at what it would take to do that, we would have to add something like HCl, which is going to add Cl to the left side of this equation. Okay, does this make some sense? All right, this is kind of the basis of titration here. So we're going to continue with this CB minus CA deal. And really the units here are essentially charge equivalents per liter. That's because we're deriving this from our electroneutrality equation, right? It's the ENA is where we're starting. So if we have CB minus CA on the left and this A minus, we can put it in different forms on the right. The left side of the equation, the units, if we take a look, are going to be the essentially net strong base per liter. That's how we'll define it. So it might be one equivalent positive charge per mole of H plus times H plus. Add that to one equivalent positive charge per mole of Na plus, and so on. The right-hand side, these are equivalents of net charge carried by the non-spectator ions. So I'm just saying we can look at all of this in a charge, like a charge equivalence perspective. That's all I'm saying here, because it's coming from this electroneutrality equation. Okay, so to define a little bit more this, the left side of our equation here, so the right side units become equivalents of basic species per liter. So we can call them, we said these are titratable by bases, or by an acid, so they're kind of the basic stuff. On the left side, these are species that can, excuse me, this is talking about the right. Sorry, I got myself confused. These are the non-spectator ions. I was like thinking we're talking on the left side. But this is the non-spectator, that's all on the right side. Okay, so on the right side, these are all species that accept one or more protons. That's kind of the definition. That's the whole conversation I was talking about by titrating them, by adding a proton, they can accept it. Okay, so let's consider some groundwater that upon analysis, we see it's got some sodium, some chloride, some calcium, and carbonate species in the CO2 system. So kind of an elaboration of what I sketched up for you already. So on the left side, we'll have, of the electroneutrality, we will have H plus Na plus, 2 times Ca2 plus. So again, we're doing charge equivalence. We have to have the 2 there. That's on the left side of the electron neutrality, so that's all of our cations. And on the right side, we've got HCO3 minus, 2 times CO3 2 minus, OH minus, and Cl minus. So when we rearrange that to get our net strong base set up, we'll have sodium plus 2 times the calcium plus our Cl minus, and on the right side we get the HCO3, the 2 CO3 2 minus, thanks, and the OH minus minus the H plus. So really just kind of what I've already talked about, with perhaps a slightly more realistic setting there. So in case my writing was not very clear, you got it here again. So everything on the right accepts 1 or more protons. Everything on the left is just hanging out. And its charge equivalence per liter is our units. So on the right, we can kind of say that's equivalence of basic species per liter if we sum all that together. All right, so the Cb minus C8 in this system, we said it looks like that. We can write it one way or the other. We can write it as equal to that right side, or we can say Cb minus Ca is equal to what's on that left side, right? So that's 2 ways to look at the equation. If we have information anywhere about Cb minus Ca, maybe from an experiment like a titration, then we know what's on the other side of that equation, right? So maybe we do a titration experiment where we're measuring the stuff on the left side, maybe that's easier to measure, then we can know the sum over here on the right side. Okay, that's kind of the deal. So we use it very often. Of course, sometimes we use this in the electron neutrality just that way. Sometimes people will even write the electron neutrality by default in this net strong base format. It's still an electron neutrality equation, right? We just did a little algebra to it. We just rearranged it. It's still the providing us the fundamental net charge is 0. It's from that relationship. Okay, so let's take a look on graphs then. So if we have this equation that we keep talking about, we'll notice that the net strong base, NSB here, can be positive, can be negative, can be 0. So where do we start? Well, if the net strong base is 0, then this, essentially, if we had no acid, then it would be at 7, right? pH 7, because the OH minus would be equal to, OH minus minus H plus would be 0. So if we had no acid, we're at 0. If we do have some acid, well, where does that net strong base equal 0? That's when the addition of these two is equal to H plus. So just thinking about it graphically, if we find a spot where the A minus, that's this guy, right? A minus plus OH minus, when we find a spot where that equals H plus, we're at 0. So let's take a look at the graph. We have A minus here and OH minus here. When we think about adding these two together, the one that's most important is the bigger one, right? So let's take a look at the graph and see which one's bigger for most spots. Well, starting in the basic condition, the OH minus gets very large over in this region, and compared to the A minus, it's actually really only in this region where it's the dominant species. So if we then say, is that equal to the H plus? Well, the H plus in this region is very, very small, so no, we're nowhere near equal. So we're going to follow the dominant species over until we're crossing where it meets the H plus. This is how we're finding the HA equivalence point. So we're going to follow this line, the H plus line, and either this line or this line, whichever one is larger, until they meet. Okay, well, as soon as we left this area, the OH minus becomes very small, so it's kind of like this is not existent anymore, right? It's like thousands of times smaller, millions. We've got a very big difference here. So we're going to follow A minus then, and then, oh, we just landed right here, they crossed. Hey, that's our equivalence point. So our equivalence point is, by definition, our starting point for this net strong base stuff. Okay, so we kind of just went full circle. We started talking about this nebulous HA equivalence point thing. Then we talked about this net strong base, and now we see on the graph, we're coming right back to it. So, given that, I'm just going to write this a little more clearly. We're going to find when the A minus plus OH minus equals H plus for the net strong base to be equal to 0. So just a nice little call out there to figure out where do we start with this, right? So the net strong base will be 0 right there. So that's why I write here at the HA equivalence point, the net strong base is 0. Now, anytime we are at any pH greater than that, we are at a more basic condition, therefore our net strong base is positive. Anytime we are below that, we are more acidic than the HA equivalence point, so our net strong base is negative, meaning we have net strong acid, essentially. Okay, so Cb minus Ca is net strong base. We could write that Ca minus Cb as a net strong acid. Just have to rearrange a few things. We could look at it either way. The convention is typically net strong base, and if you ever notice in chemistry, the convention is usually we're adding some base to our titrate, to titrate something. We're usually going from an acidic condition upwards. That's just convention. Okay. Net strong base is equal to negative net strong acid. All right. So this graph is kind of a repeat here, but it's got a little more text up at the top, so you can notice the solution of HA at the HA equivalence point, Cb minus Ca equals 0. It's got these parts labeled. At the NaA equivalence point, the Cb minus Ca is equal to, in this case, 10 to the minus 3. That's because our AT, in this case, is 10 to the minus 3, which was also shown down here. So we actually know that the NaA equivalence point, the net strong base that we have to add to get there from a net strong base of 0 is exactly the amount of acid in this solution, of the acid in question, not the strong acid, right? Or not the strong base, or whatever it is. It's the one that we've drawn on here, the HA. So the total HA, that value is the amount of acid we have to add to get from our HA equivalence point to the NaA equivalence point. We have to add that much base to get there. So we actually already said the inverse of that earlier. To go from NaA to HA equivalence point, we have to add that much acid. So, but now I think putting it in terms of the Cb minus Ca, that gives us a little bit more of a tool to say, oh, okay, now we know if we've been adding NaOH as a base, we simply need to know how much Na we just added, and we'll know if we watch what happens in the system, then we can know, we've reached the point. And by watched what happens in the system, sometimes we can monitor how much the pH changes as we're titrating something with a small addition of acid or base. If we get not much change, that means we're titrating something. If we get a 1-to-1 change, we add 1 unit of acid or base, then we change the pH by the same unit. that means we're no longer titrating something. It's just simply shifting the water. So titration is kind of getting past that point where something is shifting based on that. Like we are titrating the acids or the bases. Okay. So another thing you can notice is if we're adding HCl, that's heading us in this direction. If we're adding a strong base like NaOH, we're heading in the right direction, up the pH scale. This particular one was drawn with a pKa of some acid with a pKa of 5, right there. Okay, any questions? Just making some sense? Sort of? Okay. There's one other way that people like to describe this, at least in some of the textbooks. I don't think they mentioned this in ours, but the one that ours is based off of talks about this, and I think it's kind of useful. Some people will describe the fraction of acid or base that is in the solution as F or G. So if we define a concentration as the total acid AT in solution, but given that we are adding the titrant, usually we're changing the volume a little bit. We're not going to call it AT. It's basically AT, but maybe we want to change it a little bit or account for it. So we're going to call it C. So F then is CB over C. That's the equivalent fraction of base added, which if we're adding sodium hydroxide would just be Na plus over the total amount of acid in solution of the, I guess, the weak acid or whatever we're looking at. Likewise, G would be the total fraction of acid. Same deal, this would be just Ca over C, where C is that the AT in the given volume that we have. So if we want to account for the volume, we could do that. You know, if you recall doing the titration, you probably have some burette thing and you just drip a little bit and you watch, and it's got this like, it's kind of like a graduated cylinder, but a thin one, so you can see very clearly how much volume has changed. You're dripping until some volume, and you're like, oh, okay, it took this amount, 3.3 milliliters before this stuff changed color. Well, that's your titration, and now you've just added that much volume to your solution, so you'll usually use like 100 milliliters of solution, so it's a pretty small change in volume, but it's like, you know, 2 to 3% change. So we can change that volume and account for the new A total by doing this. It's very simple. We can just say, all right, how much volume did we start with? And how much volume did we end with? And let's just adapt, right? So really, all this is saying is if we define it very carefully, we can use F and G as these fractions that talk about what fraction of the current volume is this strong acid compared to the acid we're analyzing, the HA. Okay, all that to say, we can then use these fractions to tell us something about the equivalence points, where at the HA equivalence point, the F is 1, so F is the equivalent amount of base added, so, and G is 0, and likewise the NaA equivalence point, F is 0 and G is 1. Okay, and I think that's the amount, the fraction that we need to, let's see, would that be to get there? It's 1. I might have gotten that backwards. I'm going to double check that because it's feeling backwards right now, but I'm, you know, standing in front of you all, so I will double check this and get it right on the slides for you when I repost them. So I'll come back through and clarify that because I'm questioning myself right now. Regardless, G would be 1 minus F because these will just be the fractions kind of going between the equivalence points. So sometimes you'll see graphs where it just is showing the equivalence point as in terms of F and G as the x-axis instead of pH. It's just a little bit convenient that way sometimes. Don't bother too much with it. I just wanted to point out that we can and do sometimes account for the volume change, and we can and do use a simplified F or G scheme to describe how far along that are we. Okay, so let's try a quick example. I've got the solution up here, so take a look with me at the problem, give it a couple minutes to think about it, and then we'll work through the solution that's provided. So calculating the pH and the CB minus CA and acid-base alpha value for this scenario. So for the system, I think I had that figure. Okay, I think the figure's here, so I'll copy it over here again. I'll read it first and then I'll do that. So using this figure, we have a Ka of 10 to the minus 5. In fact, this should be the same figure right here. At is 10 to the minus 3. Some strong base is added to solution at the HA equivalence point. The value of alpha 0 is lowered to 0.3. Assume 25 Celsius, 1 atmosphere pressure, and that the activities can be neglected. What is the pH is part A, and B, how many equivalents of strong base per liter need to be added to accomplish this change? So give that a moment to think. I know we haven't really, put all the pieces together, so just see what you can come up with. I'm going to copy this graph back over, so just take a moment. All right, let's see what sense we can make of this. How do you feel, first of all? A little lost? Yeah. I mean, me too, because that's why I put the solutions there without, I'll cover them up if I'm like, oh yeah, I can teach that no problem, but I'll leave them uncovered if I'm like, yeah, let's walk through this together and see if we can make sense of it, right? Okay, so my first thought is, okay, let's take this CB minus CA formula. We were told that the alpha fraction changed, right? So we know, graphically at least, we could take a look and say we started at the HA equivalence point, and we changed from whatever the alpha fraction there between this guy and this guy was to 0.7, to 0.3 rather. So we're moving such that, alpha 0 is the HA over A total, right? And alpha 1 is A minus over A total. So we move to the point where if alpha 0 goes to 0.3, then alpha 1 is 0.7. So the ratio over here should have inverted from something to a 0.7, something like that. So we can visually think about it. We moved somewhere over in this vicinity, because we also know that this spot is each of the alpha equals 0.5, right? Alpha 1 and 2 are the same at 0.5, right? So we know that, and so we know we shifted just a little bit to the right of that. So we could make a guess at the pH just from that. But there's probably a better way to do it. And if we take a glance at the solution, it looks like there's a better way, right? Yeah.
You're kind of going with the convention that since alpha naught is 0.3 and not 0.5, and knowing that you added a base, it's going to increase the pH. So it's going to be in between the pKa and where the equivalence point was.
Yeah, it's going to be to the right of the pKa, because we went from the acidic condition where it was mostly HA, so alpha 0 was close to 1 or high, and it said now we moved to alpha 0 is 0.3. That means the new alpha 1 should be 0.7, right? So we know this should be 0.7 because alpha 1 plus alpha 0 equals 1, right? So therefore, the new alpha 1 equals 0.7, and alpha 0 was given at 0.3. So I knew that we moved to the right and we had to go further than the pKa, because as we go all the way to the right, alpha 1 becomes approximately 1 way out here, right? So we're in that transition zone still. We're not quite at the point where it's basically 1, but we are definitely to the right of that equal point where they're both 0.5. So just on the visual basis, that's how I like to start it, right? To say, okay, what can I think about the graphically? What can we say? And we could make a decent guess, right? Something like, this is a log plot, so maybe I'll exaggerate it a little bit. Maybe something right around here. pH, I'm going to say 5.6 or something. Now, the other thing we could do is take a little bit more of a mathematical approach and see if we can put in those numbers. So that's why I was thinking, okay, well, the CB minus CA equation, we know that's A minus plus OH minus minus H plus. So perhaps we can get this in the form of H plus. We're asked, first of all, what is the pH? And, as I think about it, first of all, I put this into alpha 1 times AT, so we could continue and say, okay, well, because I said alpha 1 should be 0.7, we could look at that and maybe solve from here somehow, but this is getting a little complicated because, well, we could put OH minus in terms of H plus, but we don't know what's on the other side of this equation, CB minus CA. We don't know that yet. And the question asked for us to solve for that second, so I'm not even going to try to go there yet. Okay, so the other thing I remember is, well, we have the alpha fraction and we have the pKa. So we should be able to solve for the H plus. Even the first couple lectures of class, we should have been able to do that, right? We recognize that the alpha fraction is telling us something, alpha 0, that's going to be coming from the equilibrium equation, right? Our Ka is H plus times A minus divided by HA. And we've derived this a few times now, but we can derive the alpha fraction in terms of this by doing a little substitution, right? We can say this is going to be, let's just put it in terms of, let's see. Well, let's also say the alpha fraction, right? So the alpha, we'll just use alpha 0 because that's what the book is doing, I think. Alpha 0 should be HA over HA plus A minus. Okay, that's A total. So merging these two equations, we can get a new equation for alpha in terms of pH and Ka. So that means we could solve for the H plus in terms of the alpha and the Ka. So what I'm going to do is try to rearrange this so that with these two systems of equations, my only unknown then is H plus. Okay, so for this one on the bottom, I'm going to divide the top and the bottom by H plus, and I'm just going to just kill the video feed for a moment so I can use some extra space. You guys don't notice that, but on the recording you'll see. Okay, let's get that out of my way. All right, so let's do this. Let's say this becomes 1 over 1 plus A minus divided by HA. Okay, that's just dividing the top and the bottom by HA. Now, with this, we can get the Ka equation to substitute in there, because if we divide both sides by H plus, we get Ka over H plus. So we can rewrite this to say this is the same thing as saying 1 over 1 plus Ka over H plus. Now, this is a little bit annoying to solve from there into H plus, but we can do it, right? So we could say all of this is equal to alpha 0. So I'm just going to say, simplify from there, right? So I'm going to multiply both sides by that denominator and say 1 plus 1 over, 1 plus Ka over H plus times alpha 0 is equal to 1. So I could rearrange, divide both sides by the alpha 0 and say 1 plus Ka over H plus equals 1 over alpha 0 minus 1. That'll move this over there. And then ultimately solve for H plus. So H plus would then be, I'd multiply both sides by H plus, divide both sides by all this. So that should be Ka over 1 over alpha 0 minus 1. Okay, I think I did all that right. It's a bunch of algebra, right? And what we can say, can then look at, and maybe there's a simpler, faster way to do it, but let's see if that's essentially what was going on here, and perhaps I just way overshot what I needed to do. So they write up H plus is equal to 0.3, that's alpha 0, times H plus 0.3 times Ka. Now, is that the same thing as what I have over here?
They factored it, right? Multiplied to 0.3 times H
That sounds correct, but I'm not following exactly, which is probably just me being slow. They factored this?
No,
They just multiply that
no,
across, or hang on,
I was just saying like with the original A naught, alpha naught equation.
right here?
Yeah.
Yeah, so
Or that it was just.
so what did they do to it, you're saying?
I was looking at what they put, like the H plus over H plus plus KA.
Okay, so they just started here, right? And so they started essentially, okay, so they factored, though, they multiplied the top and the bottom by H plus here. So that was a simplification that got them to the answer a little quicker or more conveniently. I'm gonna bet, if I did the algebra right, that this form is the same as this form, and that my end equation for H plus will get us to the same spot, but it's just a little more awkward.
Yeah, because ultimately, if you just multiply by H, if you multiplied that 1 over
Yeah,
1 over 1 by just H plus, you would get that.
then we get that. Yep. Okay, so that's what they did. Great. And then you can see you can solve for H plus, right? So all of that was just using these pieces that we've known since early on in this class to solve for that H plus. Okay, so from there, we're about out of time, but from there they calculate that H plus, and with that, we can just put in the numbers and solve for the CB minus CA. Okay, so it felt a lot more complicated than it needed to be, and what we'll see is the pH that they found, 5.37. My guess wasn't too bad. You know, just eyeballing, I said 5.6. Not too far off. Okay. We will talk about Excel next time. There's a few more slides I probably had here, but we'll get there next full lecture.